Good morning. Welcome to lecture 20. Today we're going to start on graph theory. Graph theory is really a lot of fun. It's something that occurs in a large variety of areas in computer science, that's for sure. And you actually encounter it every day of your lives, whether you think about it or not. So before we jump in, let's make a few announcements. This is a reminder that a week from today on Tuesday is Quiz 5. Quiz 5 will cover chapters 5 and 6 during class time as usual on Tuesday, April 20th, 10:45 to 12:05. They have to be submitted via Gradescope by 12:35. Remember, if for some reason you cannot submit through Gradescope, then you are supposed to email it to TA Ben Coverston, whose email is listed in the exam rules. And that should be done by 12:35 as well. Anything after that is late. If you're emailing it to him, it has to be by 12:35 of the clock on his email. So don't wait till the last second. We have 2 review sessions for Quiz 5 coming up. Since Quiz 5 is on Tuesday this time, remember, Tuesday, not Thursday, Tuesday. Friday the 16th, that's this Friday, at 2 p.m., James will do a review session starting at 2 o'clock. Use the Zoom for his office hours. And on Monday the 19th, Nancy will do a review session starting at 5:30. So somewhere in there, I hope whoever needs help can go. Remember, we have all the regular office hours the rest of this week, so you can come and ask questions. Okay. Are there any other questions right now? Okay, let's jump into a quick review of some of the material in chapters 5 and 6. Well, this is just 6. There were a lot of questions about one of the homework problems, and so I wanted to go through some of the issues. Now, unfortunately, my iPencil has gone in the way of, people's socks when they get lost in the wash. Well, my iPencil just got lost somewhere. So today, we're going to be going back and forth a little less interactively, but still doing pretty well, I think. A random variable is a measure of some numerical value, remember, associated with the possibility, with all the possible outcomes of a probability experiment. Okay. And given a random variable x that has n numbers attached to it, then the expected value of x is just the sum of the values times the expected value. Okay? All right. Let's continue here. Now, in Bernoulli trials, remember we have 2 random variables and we have Bernoulli trials. Each trial is an independent experiment. We have all sorts of rules, but the bottom line of it is that if z is a random variable such that z equals 0 and z equal 1 means success, and there's success with probability p, then the expected value of z is 0 times probability z is 0 plus 1 times probability z equal 1, which gives you p. And given the linear of adding them all together, we have the expected value of x is this expected value of the sum, which are the sum of the expected values. And since they're all the same, that should be n times p here. I'm sorry, that's a mistake. It's a typo. N times p. Okay. So let's go over, last time we had this practice problem that had a 3-person committee. And the club had 30 men and 20 women, and ask what's the expected value of women to be on the committee. Now, I have a couple of different ways of looking at this here. In the first way is what we went over the other day, where we just evaluated the expected value. Now, suppose we didn't know the number of women on the committee. That should shriek to you that it's like a problem on your homework. So suppose we had a club that had 30 men and an unknown number, say W women. And we ask, what is the number of women in the club so that the expected value would be 2, let's say. So we want to have 2 women on the committee. So we jump down to the bottom here to the word suppose. Then we would write 2 is the expected value of X. And that would be 0 times the probability that there were 0 women on the committee. And we just left that off. Plus 1, that's the value, 1 woman on the committee, times the combinations of W women taken one at a time. And the probability is then take that and divide by the combinations of 30, the number of men, plus W. That's the total number of people. Take 3, choose 3, times the men. And then we go through this process here and we come out with it. That's times 30, choose 2. So those two together multiply, divided by the combinations of 30 plus W taken 2 at a time. And then we go through and we figure out, well, suppose there's supposed to be 2 women on the committee. Okay, then the probability would be C of the number of women, choose 2, times the combinations of 30, choose 1, divided by the combinations of 30 plus W, choose 3. And finally, what if they're all women? And if you look at that and figure that out, you come up with an ugly cubic equation in the numerator and the denominator. And when you solve it, you turn out to find that that should be 60 women. Now, how are you going to solve it? Well, you can solve cubic equations in closed forms, and there are formulas for it. But the other way to do it is if you have Mathematica or MATLAB or access to them, which you do through the university, they will solve it for you. Okay, so if we go on from that, we look at your homework problem. And your homework problem shrieks the same thing, except now we're asking the number of seniors. When there are 10 juniors, we ask how many seniors so that there will be 2 seniors on the committee. What's the expected value to have 2 seniors? So in that case, we've got lots of lines here. Okay, so let's go through it. We let X be the random variable representing the number of seniors on the committee. And S is the total number of seniors in the club. So the total number of people in the club is S plus 10. And so we figure out the probability that there are no seniors on the committee. That's X equals 0. That there's 1 senior on the committee. That there are 2 seniors on the committee. And that it's all seniors. And then we plug that in to the equation for the expected value and say, well, that's supposed to equal 2. And you see here, I show the ugly equation that's cubic in the numerator and cubic in the denominator. And I solve it for you here. And it turns out that there are 3 roots to this. 2 are negative and 1 is 20. And 20 is the only valid one. You can't have negative seniors in a club. Okay, so that's the way you solve when you're asked, when you're told what you want the expected value to be. You have to set the problem up so that your random value represents the number of people or things that you're talking about. Let me go on. Let's start some new material here. Okay, so probability, a lot of probability, not probability, graph theory sort of arose. Euler is a very famous Swiss mathematician. And he pondered the thought one time that he was in the village of Königsberg. And Königsberg is divided into 4 different land masses separated by this river. And there are 7 bridges connecting these various land masses. And the question that he posed was, is it possible to take a walk in Königsberg using each of the 7 bridges exactly one time? You can go on the same landmass multiple times, but you can only cross the bridge once. That's the question, okay? And that led to a bunch of mathematics, which today we call Oilerian graphs and Oilerian graph theorems, okay? So the first thing you want to do is take this problem and look at it, and let's make an arrow diagram, but not arrow diagram, a line diagram. So we look at each of the 4 land bodies, A, B, C, and D, and we make them points. And then we look at the bridges, and that means we connect up, for example, C is connected to D exactly one time. So we call that edge 1. And C is connected to A 2 times. So that's 2 bridges, and there were 2 arcs, 2 and 3. Okay, so each bridge is represented by an arc or a line in this graph. And A is connected to B with 2 lines. We'll call those lines 6 and 7. And B is connected to D with 1 line. So that's the question. Can it be done? Now, this reeks of another problem that you've had. It's the same idea, a little different, which says, can you, if you draw the back of an envelope with all the various lines, can you draw the whole thing without lifting your pencil once and without going over any of the lines more than once? Okay, so these are related problems, and we're going to solve the envelope problem after we learn some things about graph theory. Okay, so what's our terminology here? Our terminology is that a graph that represents lots of real world things. So maps can be viewed as graphs, which we have a small example of on this page. Social networks are definitely graphs. Lots of different things end up being represented as graphs, and they're complex kinds of graphs. And your life is involved in those. Okay, so our simple graphs that we're going to talk about are no one near the number of things that can happen. Dane, yes.
Will we be doing any topology?
We are not doing topology. Graph theory is not related to topology.
Oh, okay.
Okay. Besides which, there are lots of kinds of topology, all of which I find interesting, but not for this class, okay? All right, good question. So a graph is defined to consist of 2 elements, 2 sets. One is the set V, and those are called the vertices or nodes of the graph. And one are the sets E, and those are the edges. And typically we talk about the edges connecting the nodes. So in our bridges, we had the bridges connecting the land masses. So those are edges. Sometimes you can think of edges as being like one-way streets. Okay, they're directed. And in a graph that has its edges that are one-way streets, they go from one node to another. And they're ordered pairs that represent an edge. Notice ordered pairs. And how do we represent ordered pairs? Well, the same way you represent the from node is first and the to node is second, parentheses separated by a comma. Okay. You can also attach weights to them. So in this picture, you can think of those as the kilometers between Madrid and Paris by one flight direction or one route. Whereas the Paris to Madrid, that's a separate route. Say they're one-way roads or something. They're separate routes and they have different distances. Or you could think of them as being a weighting, that it costs more to fly from Paris to Madrid than it costs to fly from Madrid to Paris. So the weight function is usually called the cost, no matter what it represents. Okay. Also, edges can have weights, even though they may not be directed. Okay. So if we're flying between Salt Lake City and New York, okay, you may go there via Denver, say, and it might be a lot cheaper to fly from Salt Lake to New York via Denver. Not that that shows up in your fare, and it might be more expensive to go nonstop, either direction I'm talking about. So that might be where you have two different cost functions. Notice you can have more than one edge between two nodes, and you can have zero edges between two nodes. Okay. Okay. So a graph that doesn't have directions attached to its edges is called an undirected graph. And the way they're represented is by an unordered pair. And you say, wait a minute, pair sounds ordered. No, an unordered pair you can represent as being a set of the two elements that make up the edge. Like in this case, we might write curly brace Madrid, comma, Paris, end of curly brace. Or we might have noticed that we have edge 6 is from Paris to Paris, and we might say Paris, Paris. Or you can represent it by square brackets, and we'll have some examples. But you never use the ordered pair notation of parentheses. Never, never. If you use parentheses, it means that it's a directed pair. So an unordered graph does not have directed pairs. Okay. This particular graph, we see that the edges are just numbered to show where they are. And you can have multiple edges. Now, a graph without loops or multiple edges is called simple. Okay, so that means there's only one edge connecting, at most one edge connecting any two vertices, and there are no loops from a vertex to itself. Now, we've got a lot of terminology here. So a walk is a list of alternating vertices and edges where each edge connects to neighboring vertices. So here we might have a walk that says Rome 2, Paris 1, Madrid. Notice we always start and end with a vertex, and we're going to Rome in this case on edge 2, not edge 3. So this is a way of distinguishing. So the notation for walks works whether we have a simple graph or a multigraph, a graph with parallel edges, multiple edges. Frequently, when we have a simple graph, namely there's only at most one edge between any two nodes, we don't use the edge labeling because that way we know what edge it is. There's only one, okay? The length of a walk is the number of edges. So in the example I gave, the length of that walk is 2. Okay, Now you can have, in this particular multigraph, you might have Paris 6 Paris, and that's a walk of length 1. Okay. Wow, I'm missing a bunch of questions here. Yes, lecture 19 had those slides. I wanted to go over those examples. You're right. Okay. All right, let's go on. Now, a trail is a special kind of walk. It's a walk with no repeated edges. So in this example, if I said Rome 3, Madrid 1, I'm sorry, Madrid 1, Paris 1, Madrid, that would be a walk, but it would not be a trail because I would have walked edge 1 2 times. Okay, so a path is a walk with no repeated vertices. Remember, walks have 2 components, edges and vertices. So a trail is a walk with no repeated edges, and a path is a walk with no repeated vertices. Okay, so a path can have repeated edges, kind of, but no repeated vertices. Okay, that's hard to think of, but still. Okay, a circuit is a closed trail. Okay, so remember, it's a closed trail. So I could walk, let's say, no repeated edges. I could walk Paris 1, Madrid 3, Rome 2, Paris 5, Rome. That would be a trail because I had no repeated edges. It would not be a path because I went to Paris twice. I started in Paris and I stopped there and left, and I went to Rome and I left there and then ended up. So that would be a trail, but not a path. Okay. A trivial circuit is a circuit with one vertex and no edges. Okay. You look at that and say, well, if it has no edges, how can it be a trail? Remember, a trail just says there are no repeated edges. So if there are no edges at all, there are definitely no repeated edges. So that satisfies the definition. Now, a trail or a circuit is called Eulerian if it uses every edge in the graph. Now you see this is our bridge of Königsberg, okay? Remember, our edges there were the bridges, and we wanted to go over every bridge. Now, a cycle is a non-trivial closed trail in which the only repeated vertex is the first and last one. Okay. I don't have a good example on this graph. Okay. So it's a trail. So that means there are no repeated edges. And the only repeated vertex is the first and last one. So that says we always end up where we start out. Okay, now a circuit does that as well. Okay, but a circuit can have repeated vertices. A cycle cannot. That's the difference between them. These are tons of definitions that I assume you're not too familiar with. So someone asked, is Madrid 1 to Paris 2 to Rome 3 to Madrid? Is that a cycle? No, well, Paris would go 1 to Paris, 1, 2, 3. Yes, that is a cycle. Paris 6, Paris is 2, right. That is a cycle as well. Yes. Very good. Good job. Okay, so here's practice problem 3. I'm going to give you a minute to work on and then we're going to proceed. So this says, draw the graph G with vertices A, B, C, D, E, F, and edges that connect A and B, A and C, A and E, and A and F, B and D, B and E, C and D, C and F. Okay, 4 vertices. 1, 2, 3, 4, 5, 6, 7, 8 edges. Okay, notice that these are set notation, so this is an undirected graph. So I'll give you a couple minutes for that. This is not the same graph that was in the pre-recorded lecture, so you got to draw this one.
And Dr. Cohn, there's a question in chat about the previous problem and whether Paris 6 Paris would be a cycle because it would be non-trivial.
Non-trivial closed trail. Well, remember we had that a trail with 1 vertex and no edges was defined as a trail. Non-trivial means that it's got an edge at least, and this has an edge and it's closed, and the only repeated vertex is the first and the last. So yes, it's a cycle. A trivial circuit has 1 vertex and no edges. The example of Paris 6 Paris does have an edge. Thank you. Whoops. Okay, let's draw our graph. There's the graph. Okay. Did everybody draw that one? Good. Let me get my questions up here. Okay, that's a fairly simple graph. We're going to come back to that one in a little bit. Can anyone give me a yes, you could always should avoid crossing edges when drawing graphs whenever you can. Any graph that allows you to allows you, not you personally, allows itself to be drawn on a piece of paper without crossing edges is called a planar graph. Okay. Now, sometimes you have to make really weird edges in order to make it work, but it can be done. So our examples right now, we'll see which ones can be done.
And do those have to be straight edges?
No, they do not have to be straight edges. Whether they're curves or straight, sometimes it's impossible to draw it with straight edges and still not have them cross. Okay, now the example I just drew here, I drew E and F on the inside. You could equally well have drawn E like a cap and F like a beak, for example, and that would have been a perfectly valid example of the graph. It would have all the same connections and it would be fine. Okay, so there's not just one way to draw a graph. Okay. Here's another practice problem. Okay, we got lots of questions. How many nodes are in V? How many vertices are in this graph? Count them up.
10.
10, very good. How many edges are in this graph? You're close.
20.
15 isn't quite it.
20.
Good. Who said 20?
Me, Tyler.
Good job, Tyler. Is this a directed graph, a digraph? Why isn't it? Because there's
No direction.
arrows on the edges. So we have lots of phrasing here. There's a digraph, which you've had. There's something called a DAG, and a DAG is directed acyclic graph. And that's a graph that doesn't have any cycles in it and is directed. So what does it mean if there's no cycles? It means you can't get back to where you started. That's what it felt like one time when I was driving in Washington, D.C., and they were all one-way streets, and I couldn't figure out, because I made a wrong turn, I couldn't figure out how to get back to where I started. It felt just like that. Okay. Tell me how you would specify the edge between the vertices A and B. Write it in the chat, somebody. How would you specify that? Since I don't have my pencil, I can't write it. Yes, very good. There's a single edge, and it's curly braces A, comma B, curly brace, end curly brace. Now, what if I wrote curly brace B, comma A, curly end curly brace? Would that be correct? The answer is yes, because it's not an ordered set. Either way is fine. You can go from A to B or B to A. Okay. Is this graph simple? Are there any two vertices that have more than one edge going between them? No. So yes, it is a simple graph. Does everybody see that? Good. Now, somebody, either out loud or in the chat box, give me a walk. There are many, by the way, so there'll be a lot of correct answers. From vertex B, that's on our upper left, to vertex J, which is on our lower right. So somebody type one in there and then tell me. Yeah, don't put the curly braces around them, by the way. So now we're not talking, no, not like that either. Just say the vertices labeled between them right now. If you put BI and IJ, those are edges. So let's just make a list of vertices to give this, okay? Okay, so someone says go from B to A to D to F to C. Oh, we're taking a long route here. To E, to G, to H, to J. Good. That is indeed a walk. Is it a trail? Did we go over any edge? No. Every edge that we traversed, we did it just one time. Here's one. B to I to J. Yeah, that's a direct one. Very good. They are both trails. One has length 2 because they're 2 edges, and one is a lot longer. Let's see how many edges. 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. Okay. What's the shortest length cycle? By the way, there's more than one.
3.
I'm sorry?
It's a 3. The length is 3 for the shortest.
Yes, tell me what the vertices are.
B, E, G, B.
B, E, G, B. Very good. Okay. It's of length 3 because there are 3 edges. We start with B, we end with B. There are no vertices that are repeated in the middle, and each edge is traversed only once. So it's a trail, it's closed, and there are no repeated vertices except the first and last one. Give me a longest length cycle. Okay, here we go. B to I to J, to D, to A, to C, to F, to H, to G, to E, to B. Excellent. How long was that? 1, 2, 3, 4, 5, 6, 11 vertices. Very good. Are there
There
any?
have 10 edges.
10 edges. Yes, very good. Are there any repeat? I don't see any repeated edges in there. I don't see any repeated vertices except the first and last. So therefore, indeed, that is a long cycle. Very good. Length 10. Very good. Okay, here's a new practice problem. Okay. So here we have an example of a star-shaped thing. Notice that those edges that we see, like the edge, I wouldn't say that E and F are not connected here. Why are E and F not connected? Because E is not connected to B. E is connected to F, F is connected to G, and G is connected to B. Or E is connected to A, and A is connected to B. Or there are lots of different paths. Number of vertices, 10, the number of edges, 20, the same set of questions that we had before. Lots of examples here. Okay, we have more terminology. Take a deep breath. Does a graph require that every vertex have at least one edge connected to it? No, it does not. Just think of a lonely town out in southern Utah or in Wyoming that had airplane service and the airline disconnected it. Now it has no edges from anywhere. No way to fly there if we're looking at air routes. It's part of the graph, but it doesn't have anything connected to it. Okay. All right. An edge is said to be incident with a node V if V is the endpoint of edge E. The degree of a node denoted by a degree of V is degree of V, the number of times V appears as the endpoint of an edge. Now notice that every edge is listed in the incidence of two different vertices. It's listed in the degree of two different vertices. Okay. An edge G is connected if there is a walk between any pair of distinct nodes. Okay, if there is a walk between any pair of distinct nodes. Okay. A graph H is a subgraph of a graph G if all the nodes and edges of H are also nodes and edges of G. A connected component of a graph G is a connected subgraph H of G such that no other connected subgraph of G containing H exists. Now, if a graph is connected, okay, then it's connected subcomponent. But sometimes there are graphs that are not connected and they have different groupings of things that are connected within themselves, but not to each other. Okay. A graph G is called Eulerian if there is a circuit in G that involves every edge exactly once. Okay, now let's look at that. It's a circuit, so that means there's a trail. That means we are going over the edge exactly once, and it goes over all edges. And it's a circuit, which means it's closed. It begins and ends at the same vertex. Dane, yes.
Is a connected component of a graph an equivalence class?
That's very good. Yes, indeed. Very good.
Cool, thank you.
So you could define a relation on, let's see, let me think of this, because equivalence relation, it's not quite an equivalence relation, the connected components, because if I can get from a vertex A to a vertex D, but I don't have an edge between them, if I have to go through B, I can go A to B to C to D, but I don't have an edge from A to D. That's valid as a connected part of a graph, but it is not part of an equivalence relation.
Oh, I see. That
Okay.
makes sense.
So you don't have to have every pair of things connected the way you do in an equivalence relation. Okay. However, the connected components, the components of it, the classes of an equivalence relation all form connected components of the graph. Okay, so we have one direction from an equivalence relation. If we draw the graph of it, that is indeed, they are indeed the connected components, but the other direction does not necessarily follow. Okay?
That makes sense. Thank you.
Okay. So these are biggies right here. We have proposition 711. In any graph, if there are an odd number of edges connected to a vertex X, then X cannot be an interior vertex. That means a vertex other than a starting or stopping vertex in an Eulerian trail. What's an Eulerian trail? An Eulerian trail is a trail that goes through every vertex of a graph exactly once, but it's not necessarily a circuit. It doesn't necessarily begin and end at the same place. So an Eulerian circuit is an Eulerian trail that begins and ends at the same place. And this says that if there are odd number of edges connect to a vertex X, then X cannot be an interior vertex. Okay. And then we have theorem 2. If G is let G be a connected graph. The graph G is Eulerian if and only if every node in G has even degree. Now, that doesn't tell you how to find a trail, a circuit. It just tells you that if there are any vertices in the graph that have odd degree, it can't be Eulerian. Okay?
I'm a little confused by this definition of an interior vertex.
Yeah.
A way you could rephrase that?
Yeah, an interior vertex, for example, when we walk along a path, when we walk along a trail, okay, we go, gosh, I wish I could draw. We go from vertex A to vertex B to vertex C. And then look at B. There is an edge coming into B from A and an edge going out from B to C. Okay, that's an interior vertex.
So do we say it's interior to the path? Because like if we selected a different path.
Use trail or use
trail. So do we say it's interior to the trail? Because we could select a different trail wherein it's not an interior vertex in theory.
No, you can't. If what that says, remember, we're asking here not a trail per se. We're saying it can't be a start or other than a starting or stopping on an Eulerian trail. Okay. Now remember, an Eulerian trail goes through every edge of the graph exactly once. It can have different starting and stopping points, but it goes through every edge of the graph exactly once. So we're going to do an example shortly. Gosh, I hope.
And you can't you can't just pick arbitrary start and stop for any given graph. Like there might be a limited number
You
of options.
can if you can go through every edge of the graph once with no repeats. Okay, this doesn't say there are no trails that it can be interior, well, interior to. This says that there is no Oilerian trails. Okay, that it can be interior to. So it can be a start or a stop. Okay, if it has an odd number. What it's saying is, if you think about it, here's a vertex in the middle of a trail. That means there's something coming in and something going out. Okay, now, if I go through that vertex more than once, because let's say the degree of the vertex is 4, I might come in here, go out here, and then I might come in from a different direction and go out again using different edges. But if I have an odd number, I can't do that. It's edges connected to X, or any edge that X is an endpoint of. Remember, we don't have directed edges here. Yes, Faze.
Yeah, so just want to make sure if it's something like this is the old number, but I think this one is the interior vertex, right?
Yes, but you can't draw an Oilerian trail for me, can you?
Oh, okay, I think I got it.
Okay, the key is not whether there is a trail, but whether there's an Oilerian trail.
Oh, okay, yeah.
Okay, so yes, you can certainly make it interior to some trail, many trails, but not Oilerian, okay? The Oilerian trail has the critical thing that you must begin and end. I'm sorry, you must go through every edge exactly one time. That's the critical thing that makes an Oilerian trail different. Okay, you're going through edges one time on a trail, but Oilerian says every edge in the graph. Okay, here's an example. Let's look at graph G. What is the degree of the vertex F? Yes, someone points up 4. Indeed, there are 4 edges incident on the graph on vertex F. Is the graph H connected?
Yeah.
H is the bottom graph. Is it connected?
Oh, okay, then no.
No, it's got 2 connected subcomponents. 2 connected not components, 2 connected pieces. Is G Eulerian? How would I know that? You have to count the number of edges incident on all 10 vertices. Is CF supposed to exist? No, CF doesn't exist. I'm sorry, my drawing is lousy. You say it looks Eulerian. No. We have a quantitative way of knowing if it's Eulerian. What's our quantitative way? How many edges are incident on vertex A? 4. That's an even number. How many edges are incident on vertex B? 4. That's an even number. How many edges are incident on vertex C? 4. That's an even number. How many vertices are incident on vertex D? 4. That's an even number. How many, etc. Keep going until we get down to vertex J, and there are 4 edges incident on vertex J. Okay, so we have 10 vertices in this graph G. Each each vertex has 4 edges incident on it. How many edges are in the whole graph? The man says 20. That's correct. Very good. How do you get that? Well, let's see. You're adding up the degree of each vertex. You're adding them all up, and you know that every edge appears twice. So that means that you add up all of the degrees of the vertices and divide that by 2, and that's the number of edges in the graph. So you can compute the number of edges by locally figuring out all of the degrees of each of the vertices individually, and then adding them together and dividing by 2. And that, it turns out, is one of our next theorems. Theorem 3. Oops, wait a minute. We'll come back to that. Here's your break, 5 minutes. You can ask anything you want, but I can't draw anymore. I got to buy a new pencil, it seems. Take 5 or ask questions.
Could you go back to the slide with more graph terminology real quick? Yeah, that one.
That one. Okay. Yes.
Yeah. Thank you. I just wanted to write down one more definition. Thanks.
These slides are online. All the slides with any color but blue are already online, available to you. I do not like this new magnetic clip that charges and holds the eye pencil in place because it doesn't work. Yours works good. You love it. Well, you didn't just lose yours. Somehow I lost my eye pencil. I loved it until I lost it. I stopped loving it because I'm going to have to spend all the money for a new one. Tie a giant rock to it. The problem is if I tie a rock to it, I can't charge it. Glue it to the cell phone, and then I can't use it if I glue it to my iPad. So I can call one. Yeah, great idea. I'm waiting for the eye tags to come out so I can put one on the pencil. Yeah, is that are the eye tags real? Well, I don't know. Every blog I read says they're coming, but they haven't come yet. They're supposedly little discs that you can attach to your stuff, so when you lose them, you can find them. I mean, there are things that exist like that, but not by Apple. And, you know, every time there's going to be an Apple show or something, they talk about, the blogs all talk about, maybe eye tags are coming. They haven't come yet. My daughter will go buy them for her keys. Okay, does anyone need this slide, the terminology slide now, or can I go on and? That's where we are. Okay. Okay, let's jump back in. At the end, just before our little break, we actually figured out theorem 3 all by ourselves, but this is a real theorem. In any graph, the sum of the degrees of the vertices is equal to twice the number of edges. Okay, so if we let Mary be the number of edges and Nancy be the number of vertices, then the sum from 1 to n of the degree of v sub I, vertex I, is equal to 2 times the number of edges. Okay, and we actually already figured out a proof, since we discovered that every edge appears exactly twice when we count the degree of the vertices, one for its beginning, one for one end and one for the other end. Okay, so in any graph, the number of nodes with an odd degree is even. Can you think about how to prove that? Does anyone have an idea how to prove that? I'm just trying to prep you because next class is about proving things about graphs. Yeah, that's a good question. Right now, we're only talking about degree of a vertex in undirected graphs. So that is not a problem that we're going to talk about. Okay. So why would the number of nodes with odd degree be even? Let's think about it. Dane, were you going to ask a question or give me an answer?
I broke it down by cases, but I only have arguments for the case where the number of nodes is even. So,
The number of nodes is even.
yeah, I was going to say, suppose the number of nodes is even, and then suppose the number of nodes is odd, and then work out the cases.
Okay, well, let's start out and say, in any graph, we can divide up the nodes into the ones that have an even number, an even degree, and the ones that have an odd degree. Okay, now, if the nodes have an even degree, then even plus even is even, so they sum to an even number. And if I subtract them from the total, then the sum of the nodes with odd degrees is even. I'm sorry, yeah, so the sum has to be even. So what do I know? I know that if I add an odd and an even number, I get an odd number. Okay, so if I add 2 odd numbers, I get an even number. So if I pair up each two vertices, pair them together and then counting the degrees. So if this one's odd and this one's odd, together they add to even. This one's odd, together they add to even. So now again, I'm adding even plus even. Now, if I have one left over, then I'm going to have all of these even numbers added together plus one odd number, and that would give me a sum that's odd. But what we have here is that the sum of the degrees has to be even. So that means the number of nodes with odd degrees has to be even. I can't have that one node with an odd degree hanging out there after I pair all the other ones up. Okay? Good. So here we have another theorem that any connected non-Eulerian graph G has an Oilerian trail if and only if G has exactly two nodes of odd degree. Moreover, the trail must begin and end in these two nodes. Okay. Okay, so, okay, so what is a non-Eulerian graph again? It means that we don't have an Eulerian circuit. Okay, there is no way to go through all of the edges exactly once and end up back at the original vertex. Okay, so it has an Eulerian trail. What does that mean? It means that we can go from with a beginning vertex to an ending vertex that's different and goes through every edge in the graph. And so this theorem says that if the graph is connected and not Eulerian, it has an Eulerian trail if and only if there are exactly 2 nodes of odd degree. Remember, with the number of nodes of odd degree has to be an even number. So we're saying if there are exactly 2, then we can form an Eulerian trail using 1 as the beginning and 1 as the end. Okay, that's kind of cool. Okay, now a disconnect, notice the presumption. We have to have a connected graph. Okay, no graph that's not connected can be Eulerian because you can never go through all of the edges and start and stop at the same place or even different places because you can't get to one component from the other. There are no edges between the components. Okay, good. Here's a practice problem. Consider the walk that goes from A to C to F to A to E to B to A. What is the length of the walk? The man says 6. That's exactly right. It's 6. Is the walk closed? Do we start with A and end at A? Yes, it's closed. Is the walk a trail? Yes, we have only traversed the edges that are in there one time. Is a walk a path? Remember what a path is? No repeated vertices. Well, we definitely have repeated vertices here. The vertex A appears 3 times. The trail doesn't repeat edges. The path doesn't repeat vertices. Yes. Okay. Is the walk a circuit? Is the walk a circuit? Yeah, it begins and ends with A and it's a trail. Is the walk an Eulerian circuit? Does it use every edge in the graph? No. The edge from C to D isn't used. The edge from B to D isn't used. It is not an Eulerian circuit. Is the walk a cycle?
Yeah.
Remember what a cycle is. A cycle is a circuit whose only repeated vertex is the beginning and end vertex at the beginning and end. This one goes through A in the middle. So it repeats the vertex in the middle. So no, it uses A as an interior vertex as well as the 2 endpoints. So it is not a cycle. Good try. Is the graph Eulerian? We can answer that. Why not? Someone says no, but tell me why. Vertex C, the man says, has degree 3. That's right, an odd degree. How many vertices are there with odd degree? Degree B and degree C have, the degree of B and the degree of C are both odd. That's true. Do we have more than 2 vertices with odd degree? Yeah, no, they're just exactly 2. That means that this graph has an Oilerian trail that we can go through every vertex exactly 1 time. Okay, I, for example, might pick, let's see, we could start with B. You want to start with B? Yeah, we'll start with A, with C. We go from C to F to A to C to D to B to A to E to B. And we have gone through all of the edges exactly 1 time. Yeah, well, these definitions, there are a lot of definitions, and I understand they can be confusing. Okay, that's why we're talking about them in class. Okay, but study them. On the exam, I would definitely tell you to put this on your index cards to keep them straight.
So what's the right answer to, is it Eulerian?
It is not an Eulerian graph because not all of the vertices have even degree. As someone said, vertex C and vertex B each have degree 3. But remember, we had theorem 5. What did theorem 5 say? A connected non-Eulerian graph has an Oilerian trail if and only if G has exactly 2 nodes of odd degree. I don't know what equal/equal means. Oh, that means not equal. Ah, you're clever. Very good. Okay. Yes. Okay, good. All right. So that's practice problem 6. Practice problem 7. Now this is hard without my pencil, but we're gonna make a dash of it. Is this graph Eulerian? So someone says, no, it is not, because vertex B has degree 3. Do all the other vertices? Now remember, we have to have at least 1 other vertex that has odd degree. Why? Well, that was, let's see, that was either our corollary or that was our corollary 4. That said, the number of vertices or nodes with odd degree is an even number. So the man says degree of I is 3. Yes, that's right. Is everybody else even degree? Yes. So that says that this graph has an Oilerian trail, but is not Eulerian. Aha. Could I modify the graph to make it Eulerian? How would I do that? How would I do that? So right now, I know that I can create a trail. You're removing things. You're adding things. We got lots of things. Connect I and B, one person says. Yes. We have an Eulerian trail that goes from I to B or B to I, whichever way you want, doesn't matter. So that goes through every edge that we have now. Now, if we add an edge between B and I, can we do that without crossing it? Yeah, we just loop it around with a big arc. We go from B to I, now, so that we now have a loop. We have a circuit. It goes through every edge once. We have another edge. We added an edge, and we can get to exactly where we started from. You're thinking topological question. I'm sorry, my definition of topology may be different than yours. So if you're talking about connectedness in topology or things like that in a graph sense or a mesh sense, maybe we do talk about topology. I don't know. Okay, so we can make this graph Eulerian by adding an edge from B to I. Now, you want to add an edge from I to I and B to B, or is that not allowed? No, then you're adding two edges. Remember, you count the loop twice. It has a beginning and an edge. It's the same edge, it's incident twice. So you've just upped the degree by 2 if you add loops. Okay. Good. All right. Okay, here's a practice problem for you. Last thing of the day. Prove that for a simple graph G, in which all the n vertices have degree at least 2, that there are at least n edges. This follows pretty strongly from, I think that was theorem 3 about the sum of the degrees of each vertex. So we have n vertices, each has degree of at least 2. Prove that there are n edges. Why don't you give it a start and then we'll pick it up. So for all of you, I really like that you're asking questions about graphs because the graphs are cool and graph theory is cool. So whether we call it topology, there are lots of ways people use the word topology and they're all legit. And if I put my right hat on, I agree with all of them. So don't worry about asking questions. Okay, let's do it. Here it is. We have 2 different proofs here. So let's do the bottom one. If we let m be the number of edges, then we know that twice the number of edges is equal to the sum of the degrees of the vertices. And we know that each vertex has degree greater than or equal to 2. So the sum of all of that is greater than or equal to 2 times n. So we have that 2 times m is greater than or equal to 2 times n. So m is greater than n. And the inequality follows. That's our proof. Okay. Proofs don't have to be scary here. Is there an Eulerian circuit or an Oilerian trail for this graph? I've numbered the vertices in the graph here. That's our envelope problem. Can you draw that envelope without lifting the pencil? That's the Oilerian trail question. Can you draw it beginning and ending at the same vertex? That's the Oilerian graph problem. Eulerian circuit problem. Can we? One person says, circuit no, trail yes. Tell me why. Vertices 3 and 4 have an odd number of edges. Very good. An odd degree. Very good. Exactly right. The man says trail yes. So what do we know? We know that our Eulerian trail, I can start it at 3 and end at 4, or I can start it at 4 and end at 3. No problem either direction. It's the same trail. Okay. Very good. And there's an example from 3 to 2 to 1 to 5 to 2 to 6 to 5 to 4 to 6 to 3 to 4. Notice that that is not a path. Okay, we see 5 appearing on the inside twice, interior twice. We have 4 appearing twice, not both at the beginning and end. So it's not a path. We're going through a vertex more than once. Very good. Gosh, I've got more even, but I think we're going to quit today. And I want you to think about this as a practice proof. We'll start with this next class. A graph is connected if and only if for every pair of different vertices, A and B and G, there's a path in G starting at A and ending at B. Okay, that sort of feels like the definition. That's why it's only a lemma, not a theorem. Okay. All right. We're going to finish 2 minutes early today, everybody. I hope that you enjoy graph theory. I think it's fun. It's a little hard getting used to all the different definitions, but once you float in it for a while, it doesn't feel as weird. Just think about your social networks. If any of you are on Facebook or anything like that, they use graphs. They're all graphs. Who are your friends on Facebook? They're all the people you're connected to. You have an edge with if they're your friends. Okay. So how big are their networks? How big are their graphs? All right. Remember, homework is out. Please read the book. The book has the definition. The slides are online under class lectures, and we will resume on Thursday talking about proving things about graphs. Okay, I'll answer any questions anyone has. And I hope to have a new pencil by then. Bye-bye.
Thank you.
Thank
I
you.
just have a quick question about the quiz. So
Yes.
it's on the 20th, and then our final is a week after that, right?
On the 30th.
Oh, okay.
Yeah, the last class is the 27th, and that's a review. So we have 3 lectures on graph theory, today and Thursday, and next Thursday. Tuesday's the quiz. And then the following Tuesday is a review of the whole semester. Okay, all in one 80-minute class. And then the next Friday is the exam. I'm sorry, it's only a few days to study, but the university says that's it. So that's it.
That's okay. I usually cram the day before anyway.
Don't tell me that.
So will this next quiz cover graphs?
No, the next
Okay.
quiz is chapters 5 and 6.
Okay, I see. All right, thank
Okay.
you.
Is the final comprehensive or is it just
Yes, it is comprehensive.
is there going to
You
be
don't have to go to
roughly,
the or. The final is comprehensive.
is there going to be roughly equal weight on each section of the course?
Well, that's hard for me to answer because chapter 2 is all about proofs. And then all the other chapters we have are various proofs. So there'll be proofs, but is that chapter 2 or chapter 3 or chapter 4 or chapter 7? All depends. We use the techniques all over, so I'm not exactly sure how to phrase that. There will be proofs. How's that?
Yeah, I guess I'm just hoping for some direction on effective study strategy.
Yeah, well, I'll say one thing. I will definitely have questions about chapter 7 since that will not have been covered on any of the other quizzes. Will it be weighted heavier? I don't know. Chapter 4, we had more lectures. You know, chapter 5 was only 2 lectures and chapter 3 was what? Chapter 6 was what? 3 lectures. but there's one quiz covering and that's 5 lectures. So I think chapters 5 and 6 are so closely related. So what does it mean, equal weighting? So I will try and think about giving you some guidance on Thursday or next Tuesday. Next Thursday on the final, but right now study for the quiz 5. Okay.
Okay, thanks.